Alright, so we'll get initiated into rudiments of gravitation today. Before that, let me take you back to work power energy, where I spoke of what we refer to as a force field. Essentially, it's a region in space where a test particle can experience a force, right? That's a force field. Now, force fields basically have their own characteristics. A special kind of force field, very relevant to our current discussion, is what we refer to as a central force field. What it really means is there is a point O, a fixed point O. In this region of space, if let's say a certain particle, if in this region of space a certain particle undertakes a certain trajectory, then force that the particle experiences when it's at any point P, the force that it experiences when it's at any point P, if it's directed towards O or away from O, if it's directed towards O or away from O, that means the line of action of the force experienced by a test particle, the line of action of the force experienced by a test particle always passes through a certain point O, then this force field is referred to as a central force field. If the force experienced at any point of this field by a test particle, if the force experienced at any point P of this central force field is such that the line of action of the force will always pass through O, either it will be directed towards O or away from O, which is when we refer to this as a central force field, right? Now, at any point P, where OP is R, if the force experienced by a particle, is of the form, if the force experienced by a particle is of the form some function of R, where R is the distance from the point O to where the particle is. This is the imaginary line joining the position of the particle to a certain fixed point O. This distance is R. If the force acting at any given R depends on R, this f of R means it could be, for example, f of R could be 1 by R squared, f of R could be R cubed, f of R would be 1 by R squared plus R, it could be sine R. It's in general a function of R, where R is only the distance between the particle and the fixed point O, into, this is as far as the magnitude of the force is concerned, into a unit vector along OP, where OP is referred to as the radius vector of the particle. OP is referred to as R, the radius vector. OP cap is a unit vector along OP. Now, if f of R is positive, then realize that the direction of the force will be away from O. If f of R is negative, then the direction of the force would be towards O. Does it sound all right? So, we would have a discussion centered around a force field of this kind. It's central because of this. The direction of the force is always along the radius vector, and the magnitude of the force depending on the distance between the particle and the fixed point, depending on R, the distance between the particle and the fixed point O. So, we would focus our attention on forces of field of this nature, this nature. Now, without, right away I don't want to do that, but I'll come back to this fact. For the time being, I want to make a mention of all generic fields of this kind. All generic fields of this kind where the magnitude of the force will depend on the distance r alone and would always be along the radius vector OP. All fields of this kind would have a certain characteristic, Let's say, let's not bother about who's creating this field. Let's not bother about the source responsible towards creation of this field. But let's look at a particle which is exposed to such forces. Let's look at a particle that is exposed to a force field of this kind. Let's say there is a particle, a test particle, which undertakes a trajectory, a certain trajectory from A to B in this force field, Now, obviously, first of all, this point O, the fixed point O that I refer to as, we'll call the center. It's not like the center as in a circle, but we'll just refer to this as the center. Now, different points along the trajectory are at different distances from O. In general, different points along the trajectory are at different distances from O. Therefore, the magnitude of the force experienced by the particle in its journey from A to B along a trajectory will, in general, have a different magnitude. Because R, in general, is different for different points along the trajectory. Let's say this is R, the vector R, whose magnitude is R. Now, at any given point, the force experienced will be towards O or away from O. We say that this is like a radial field. We can call this a radial field. The line of action always passing through a fixed point O. You could loosely call it a radial field. Now, while the particle undertakes this journey from A to B along this particular trajectory, at any given point P, the force experienced by the particle F will depend on R, and the line of action of this force will pass through O. That's what entitles it to become a central field. Now, if the particle gets displaced by a small amount dr along the trajectory, after all, this entire trajectory is sum of several such drs, isn't it? Any trajectory is the vector sum of infinite number of these drs, right? All these drs put end to end will produce this trajectory, right? It's not like F is perpendicular to dr, because this is not necessarily a circle. This is not the center of a circle. So in general, F and dr will have an angle enclosed between them. But whatever be it, for a small, infinitesimally small displacement along the trajectory, the work done by the force of the field, this F is the force of the field. The work done by the force of the field, referred to as this, would be the force, because for this very small displacement, force vector remains practically constant. So the work done by the force is going to be F dot dr. That's going to be the work done by the force of the field, which is referred to as the work done by the field. We call this as the work done by the field. Work done by the forces of the field is the work done by the field. Right? Now, at every point between A and B, I can look at the force F and then a dot dr. A force F and then dot dr. A force F at this point, dot dr. And so on and so forth, right? So I can carry out a summation of F dot dr from A to B along the trajectory. I can carry out a summation of all the F dot drs, the work done by the force, from point to point, enabling a displacement dr from instant to instant, right? And when I do a F dot dr for all the points along the trajectory from A to B, I can then add up all the F dot drs, if I add up all the F dot drs from A to B, then this is what I get. Then this would be the total work done by the force of the field. This would be the total work done by the force of the field, where the vector r varies from r at A is RA, position vector at B is RB, right? RA is like the vector OA, RB is like the vector OB. So R runs from RA to RB. R runs from RA to RB. That's the work done by this field. Now, what I would demonstrate, but not right away, because otherwise, you'll get distracted from the mainstream. So I will not do that right now. I want to put you into the mainstream right away. But what I would demonstrate, possible today itself, that this integration, if the force is of that kind, if the force is central in character and of this kind, where it's a function of r, then for all forces of this kind, the work done by the field along any path between A and B, will not depend on what the path actuals were. That means if you take this path from A to B, this would be the work done. If you take any other path from A to B, the work done would also be the same. That means this work done for this kind of a field, I will demonstrate, does not depend on the actual path pursued between A and B. This integration is path independent. If, provided F is of this form, this will be a path independent entity. And if the work done by a field of this kind is path independent between A and B, then this field would be referred to as a conservative field. This would then be a conservative field. This F is a conservative field or a conservative force field, either way. Now, do you recall that conservative field? Work done in a closed path is 0. Work done in a closed path will always be 0 by the forces of the field. Number one. Number two, a conservative field will have a certain property called the potential energy at a point. Potential energy of a test particle at a point could be defined for a conservative field. Do you recall that? We had defined potential energy in a certain manner, right? So then, in a conservative field, one way to describe the field is a vector description. At every point, I can associate a force vector. That's one way to describe a field. And if it's a conservative field, every point could be related to a number. That number refers to the potential energy of a test particle at that point. Right? With every point in that field, I can associate a scalar, a number, which represents the potential energy of a test particle when placed at that point. So, the potential energy from point to point will depend on the specific position in the field, right? So, the force would be a function of the position. The potential energy would be a function of position x, y, z of the particle in that region. All right. Once we understand this, let's jump straight into our notions and basic understanding on gravitating masses. All right. But then, whatever I have said is true for fields of this kind, where the force will have a magnitude which will only depend on the distance r of the point P from O, and the line of action of the force will always pass through O. Right? If this happens, then you can be guaranteed that the field is conservative in character. Right? Now, look, let's say there is a gravitating mass n, point mass capital N, right? And let's say I pin this point at a certain position. I pin this particle at a certain position in space. Then, surrounding this mass capital M, a field of influence is created. Because if another test mass is placed in the vicinity of M in a certain region, then that test mass will experience a force, right? So there is a force field created by capital M, which is called the gravitational force field, right? Now, let's say a mass small m is placed at P at a distance r, A mass small m is placed at P at a distance r from a gravitating mass capital M. Let's say capital M is placed at O. Clear? Now, from Newton's law of gravitation, all of you know that the particle placed at P will experience a force F, whose line of action will always pass through O. And the magnitude of F is given by gmm by r squared. Gmm by r squared, right? Where g is the gravitational constant and it has a value which is like a 6.67 into 10 to the power minus 11 Newton meter squared per kilogram squared, right? You're aware of this. That's the magnitude of the force. What about the direction of the force? The direction of the force will always pass through O. Which means now, this force has a magnitude which will be a function of R alone, and the direction of this force, line of action of this force will always pass through a certain fixed point, O, where capital M is located. Therefore, is this force not exactly of the kind that we just discussed, right? In fact, in this case, this is an inverse square law field because it varies. The magnitude of the force varies as 1 by r squared. It's also called an inverse square law field. Inverse square law field. It's going as 1 by r squared. Yeah. Now, it's a conservative field. It therefore is a conservative field. So with this field, I can associate a potential energy function. At every given point. What I would now try and do is, I'll establish the potential energy at the point P of this field for a particle of mass small m. This is our test particle. This is the mass which is producing the field, right? Within the jurisdiction of the field produced by this mass m at a distance r, I'll attempt to compute the potential energy of a mass small m at P, right? Now, go back to basics, which is how I define my potential energy function. This is O, this is M. Point P, which is at a distance r. Now, the force experienced by a particle of mass small m is F, which is like gmm by r squared, leftwards, right? Now, if the particle moves to a nearby point Q, which is now like a r plus dr, if the particle is moved from P to Q, that means if the particle goes from r equal to r to r equal to r plus dr, then the work done by this force, what would be the work done by this force? That means the work done by the field. Is going to be what? The force is leftwards, the displacement is dr rightwards, right? The work done by the force then is going to be gmm by r squared into dr. That's the work done by the force, work done by the field, right? Hey, but the work done by the field was defined as the negative of the change in potential energy. Was defined as the negative of the change in potential energy, yes or no? So if the potential energy at P was U and the potential energy at Q was U plus du, then the change in potential energy from P to Q is du. Negative of the change in potential energy would be minus du. So then the work done by the field will be negative of the change in potential energy of the particle would be negative of the change in potential energy, right? That's how potential energy is defined, right? Now what we do is we integrate. We have like GU equal to GMM by R squared into dr. Let me integrate both sides. Let's say when R is R, that means when the particle is at P, the potential energy is U, a function of R. Let's say the potential energy is U, a function of R. When R is infinity, I can always define the potential energy at infinity to be 0. Who stops me from doing that, right? When R is infinity, let's say the potential energy is defined to be 0. That's my choice. I can do that, right? So then when I integrate this, I get like a minus U at R. And 1 by R squared, when you integrate, you will get minus 1 by R. So this would be like a minus GMM by R, where R runs from R to infinity, where R runs from R to infinity, right? So which would produce like the potential energy at R as GMM. Now this would be, the minus sign gets cancelled. This is like 1 by infinity minus 1 by R, right? When I supply the limits, it's 1 by infinity minus 1 by R, yes or no? It's like a minus GMM by R, because 1 by infinity is 0. So the potential energy at a distance R from a gravitating mass capital M in its own field is, for a particle of mass small m, is minus GMM by R. This is the potential energy of a mass small m. This is the potential energy of a mass small m at a distance small r from a gravitating mass capital M, right? This is potential energy of mass small m at a distance r from capital M, which is a point mass. Now we define at P. This is a certain point P. This is the potential energy of a mass small m at P. This is the potential energy of a mass small m at P. We define at P a certain property of the field. A certain property of the field. At P we define a property which is the potential energy of a unit mass at P. The potential energy of a unit mass at P is referred to as the potential at P. We define the potential at the point P, which is the potential at P, as the potential energy of a unit test mass at P. A unit test mass at P. Potential at P is defined as the potential energy of a unit test mass at P. Unit test mass means if you put small m equal to 1, you get the potential energy of a unit test mass at P. You get the potential energy of a unit test mass at P, which is like a minus Gm by R, which is like a minus Gm by So potential at a distance R from a point mass capital M will always be minus Gm by R, which will be the potential energy of a unit test mass. So for a mass small m, the potential energy would be potential into small m will give you the potential energy of a mass small m at a distance R. Now, this is one school of thought. Fundamental. This is fundamental though, right? Whatever I've said about our understanding of potentials at a point, potential energies at a point, and potentials at a point, this is how it's basically supposed to be understood. Yet, there is another school of thought in which they define potentials differently, but then it helps us arrive at the same basic result. There is another way, and I want to make sure that the convergence takes place in the class between these two schools of thought. You'll realize that it leads to the same essential, and I want you to understand that in light of the fact that a similar force field, which is the electrostatic field, will come into place down the line, and a good integration of the two kinds of field would take place on a common fabric, and whatever you learn here will actually get inherited into our understanding of electrostats, and life will become kind of smoother. All right. So, this fact you understand, potential at a distance r from a point mass capital M is this, which is potential energy of a unit test mass. Sometimes, some people prefer to define potential at a point as follows. Let's say there is a gravitational force field produced by a point mass capital M. And I want to be able to compute the potential at P. I want to be able to compute the potential. Potential at P I'll refer to as VR. VR, which is potential energy of a unit test mass, VR, right? Write down. Potential at a point is defined as the amount of work done in bringing a unit test mass by an external agent from infinity to P, to that point, from infinity to that point. Can you just read out what I said? Without adding kinetic energy to the test mass. Without adding kinetic energy to the test mass. Understand this. I have a unit mass small m equal to 1, and I want to bring it from infinity to the point P, which is at a distance r from a gravitating mass capital M, right? But I want to bring it from infinity to P without changing the kinetic energy of the particle. That means without causing the particle to get accelerated, right? Because if the particle accelerates, its kinetic energy would change. So I want an external agent to do me this favor. I want the external agent to transport a unit test mass from infinity to P without causing acceleration to the particle. Without causing acceleration. The work done by the external agent in the process will be referred to as the potential at the point P, right? So then, there's an external agent. There is an external agent which is transporting a mass from mass equal to 1 unit from infinity to P gradually, slowly, which is gradually transporting a mass m equal to 1 from infinity to the point P gradually. Now, at an intermediate point from infinity to P, the test mass m equal to 1, unit mass m equal to 1, experiences a force leftwards because of the field? Experiences a force leftwards because of the field, yes or no? Attractive force, so this is the force because of the field. attractive force because of the field, whereas the external agent must apply a force rightwards. The external agent must apply a force rightwards at this intermediate point P prime. Why? Because you want this external agent to not add kinetic energy to the particle. If F external was different from F of the field, then the particle will get accelerated, and if the particle gets accelerated, its kinetic energy would change. That means at every instant, the force of the field changes because the particle will be at different distances from capital M. So the external agent would have to accommodate its own gears commensurate, so that at every point it applies a force, the external agent at every instant P prime, it applies a force equal in magnitude to the magnitude of the force applied by the field and oppositely directed Such should be the external agent. Such should be the external agent, right? If at a given point this was different from this, then the kinetic energy would change. So basically, the particle is very cautiously moved from infinity to P, ensuring that at every point the external agent senses what the field vector F is, and accordingly it applies an equal and opposite force on the particle, and then very slowly it transports the particle from infinity to P, making sure that at every instant the particle is, the unit mass is in dynamic equilibrium, No net force, zero acceleration, no change in kinetic energy. Particle is very slowly moved from infinity to P in an unaccelerated manner, in a quasi-static manner, right? Now, so essentially the particle at every instant is being acted upon by two forces. One, the force because of the external agent. Two, the force because of the field, right? Very clearly, when the particle moves in this direction, when it inches closer to P, and it gets getting displaced towards P, then the work done by the field in this case, for example, is positive, because the force of the field is leftwards, the displacement is also leftwards, right? Whereas the work done by the external agent is negative, because the force of the external agent is rightwards, whereas its displacement is leftwards. So which means at any given instant, the work done by the field should be negative of the work done by the external agent. Any given instant, for any small displacement dr towards P, the work done by the field and the work done by the external agent must be equal in magnitude but opposite in signs, right? One of the forces is doing positive work, it's aligned towards the displacement. The other force is doing negative work, it's oppositely aligned, right? But what we are saying is essentially it's a quasi-static movement, very, very slowly. So it's like we talk of what's called dynamic equilibrium. It's called dynamic equilibrium. The particle did have kinetic energy in this direction, but then that kinetic energy was maintained constant. Let's say the particle did have some kinetic energy, and we could have maintained that kinetic energy constant by applying external forces like this, right? That's what I meant. So now, we want to make sure that acceleration is zero, kinetic energy in this transport is constant. So then, the potential at the point P, is the amount of work done by an external agent in bringing a particle from infinity to P by an external agent for a unit mass m equal to 1. Work done, unit mass m equal to 1, keeping kinetic energy equal to constant. At every point, the external agent balances the force of the field. Clear? So work done from infinity to P by an external agent, keeping kinetic energy equal to constant. Clear? Now do you realize that this must be negative of the work done from P to infinity by the field? Work done by the external agent is negative of the work done by the field if you are not adding kinetic energy to the particle, right? This is what I discussed. So this must be negative of the work done from infinity to P by the forces of the field. Again, everything else remains the same. Kinetic energy constant for a unit mass. Negative of the work done from infinity to P by the forces of the field, right? Now, realize that the work done by, for example, the field is leftwards all along. So when you are bringing the particle from infinity to P, then the work done by the field, let's say, is positive, right? You could have imagined the particle going from P to infinity, in which case, at every point, the field will be leftwards, but the displacement would be rightwards. In which case, the work done from infinity to P by the field is negative of the work done from P to infinity by the field, right? If you now imagine the particle to go from P to infinity, do you realize that the work done by the field will be negative of the work done by the field when the particle came from infinity to P? Because the force has the same direction, but now the displacements are oppositely directed. Clear? So then, can I not say that this is the work done from P to infinity by the forces of the field, keeping kinetic energy constant on a unit test mass, That will bring us to the potential at a point P. That will bring us to the potential at the point P of the gravitational field produced by capital M. Clear? So then, once we understand this, realize that when the particle is at a certain point P, a distance r, the force of the field. So I now want to compute the work done by the field from P to infinity, right? When the particle is at a certain point P, it experiences a force which is leftwards, force of the field. This is force of the field. Now I have discarded external agent because I have now reduced it to what eventually the field does. I'm interested in the field, not in the external agent, right? So then the work done, the force of the field at this point P is like a Gm, small m is 1 by r squared leftwards, Gm by small r squared leftwards. Now to take the particle from P to a nearby point P prime, displacing it by an additional amount dr, the work done by the field would be this into dr with a minus sign, right? So then I want to compute the work done from P to infinity. Work done for a small displacement by the field is like a minus Gm by r squared into dr. Yes or no? Sorry? No, the r's are like this. Why minus dr? Well, the force is leftwards, the displacement is rightwards. So angle between force and displacements is 180 degrees. So work done F dot ds na? That's why. Clear? Now, the total work done by the field from P to infinity would be sum of all of this, right? That will be the total work done by the field from P to infinity would be sum of all of this, where r runs from r to infinity, This is the work done from P to infinity by the field, and that would be defined as the potential at r, Very clearly then, when you integrate this would be minus 1 by r, so this would become like a 1 by r, where r runs from r to infinity. That will be the potential at r, right? 1 by r squared, when you integrate, it will be minus 1 by r. So then this is like a Gm into 1 by infinity minus 1 by r, which is like a minus Gm by small r. That's a potential at a distance r. boils down to the same result. So then, that was our earlier fundamental understanding of potential at a point. This is like the amount of work done in bringing a unit test mass from infinity to P by an external agent, keeping the kinetic energy unaltered, keeping the particle unaccelerated at all instants, right? It boils down to the same result. So both the schools of thoughts eventually lead to the same mathematics. And it's a scalar number, so every point of the region surrounding M can be represented by a number, which is the potential at that point minus Gm by R. For different values of R, you will have different potentials. All points at a distance small r from capital M, that means a sphere surrounding capital M will have points at the same potential. All points on a sphere surrounding capital M, centered at capital M, will have the same potential because they'll have the same value of, you know what I'm saying, right? And again, you might argue, hey, I have computed the work done by the field, taking the displacements all along the same line. What if the particle were to be displaced along a complicated trajectory? It's going to be the same because it's a conservative field. The work done by the field will not depend on the path actuals. So since it does not depend on the path actuals, might as well take the most easy path and compute the work done. Then any other path between 2 points will give you the same value of the work done by the field because it's a conservative field. Clear? Now, this was a very important thing to have understood. Potential at a point, potential energy at a point, and both the schools of thoughts in this context. Now, few things which I want to mention, again without offering formal proofs for this. One, if there is a uniform solid of mass capital M, capital M, let's say radius capital R, and there is a test mass placed at P at a distance small r greater than capital R. That means outside the sphere, there is a test mass M placed. Then, for the sake of computing the force between this sphere of mass and small m, after all, Newton's law of gravitation is valid for point masses, right? Force between point masses. Now, it can be proved that for points outside the sphere, this entire mass could be replaced. If it's a uniform solid sphere, it could be replaced by a point mass capital M placed at the center, by a point mass capital M placed at the center of the sphere. For points outside the sphere, in order to look at its gravitational influence, I can replace this entire sphere by a point mass capital M placed at the geometrical center of the sphere. And the force between this sphere and this mass M will be like a G capital M into small m by R square, right? That's one thing that you must remember. The second thing is, so this was a solid sphere, and then we distinguish a solid sphere from what we call a spherical shell. There is a spherical shell. A spherical shell is like a hollow sphere, with a very small thickness, very thin spherical shell. This is a spherical shell. Of mass capital M. This mass is contained in the shaded region. The mass is contained in the shaded region. This is the center of these shells. and the mass m is contained in this thickness, small thickness. That's a spherical shell. That's a spherical shell, right? All the mass is contained here. Now another result again which I want to offer without proof to you, and please take it lying low, because again we'll prove it in so many different ways down the line in our general digressions, but since this is going to be a compact class, I'm not going to get into those deliberations right now. But now inside this spherical shell, if you place any test mass m inside this spherical shell, if you place any test mass m, then this small m will not experience any net force because of this capital M. Because there are elements of this mass which would exert a certain kind of a force on small m, attractive, and then there would be elements of this mass having exerting a force on this small m in another direction. If you have to compute the vector sum of all the forces that various mass elements of the shell exert on small m, then the vector sum of all these forces on small m because of this shell will be 0. Force acting on this small m is going to be 0. Force on small m because of the shell is always going to be 0, That's a very important proposition. Now, we define in a gravitational field what we refer to as the intensity of the field. We define in a gravitational field what we refer to as the intensity of the field. Intensity at a point is the force experienced by a unit mass at that point. That's all. Intensity of the field at a point, intensity of a gravitational field at a point is the force experienced by a unit mass when placed at that point. Potential at a point is what? The potential energy of a unit mass at that point. Whereas intensity at a point will be force experienced by a unit mass when placed at that point. That's intensity at a point, right? Now, let's say we look at the Earth, mass capital M and radius r. Let's say there is a unit mass m equal to 1. There is a unit mass m equal to 1. Then the force experienced by this unit mass, if it's, let's say, at a distance small r outside the Earth, let's say this point P is outside the surface, then the force experienced is going to be gm by r squared. Force experienced by this unit mass is going to be gm by r squared, which is force on this mass divided by this mass. That means this is also the acceleration of a unit mass at this point. This is also the acceleration of a unit mass at this point, force divided by mass, right? The acceleration at this point is g, the acceleration due to gravity is g, the acceleration due to gravity, which is the, in general, this would be the acceleration not just of a unit mass. If the mass was small m, then the force divided by small m will still give me gm by r squared, right? So that does not depend on the mass, does not depend on the test mass. But then this for sure at this point is the intensity of the field at this point. The acceleration due to gravity at a point, is also the intensity of the gravitational field at that point, right? Now, let's quickly look into how acceleration due to gravity varies on various fronts, right? Like I said, for points P outside, you can replace the mass of the sphere by a point mass at the center O of the Earth, right? And let's say the point P is at a distance r from the center. The point P is at a distance small r from the center. Then, very clearly, if r is greater than or equal to r, which is points on or outside the surface. For small r greater than or equal to r, points on or outside the earth. On or outside the earth. The acceleration due to gravity, g, is going to be gm by r squared, is going to be gm by r squared, right? The acceleration due to gravity on the surface of the earth would be obtained by putting small r equal to capital R, the radius of the earth, which is like roughly 6,400 kilometers and so on and so forth. Now, variation of g with distance. Let's say this point is small r equal to 0, so this point represents the center of the earth. This point represents the center of the earth, small r equal to 0. This is small r equal to capital R, which is a point on the surface of the earth, which is a point on the surface of the earth. The acceleration due to gravity on the surface of the earth, let's say, is g naught, which is gm by capital R squared, which is gm by capital R squared. Which is acceleration due to gravity on the surface of the earth. Now, very clearly, as r increases, as small r increases from the surface onwards, g will decrease and g falls as 1 by r squared. So, the variation of g with distance from the center of the earth outside the earth is a 1 by r squared fall, is a 1 by r squared fall. G falls as 1 by r squared from the surface and outside, right? Now, for points inside. Now, we could also do some approximations here. Suppose this point P is at a height h above the surface of the earth, right? So, then this small r is like a capital R plus h. This small r is like a capital R plus h. H is the height above the surface of the earth. In which case, the g at a height h can be obtained by gm by r plus h whole square. G is gm by r plus h whole squared, yes or no? Which could be written as gm by r squared into 1 plus h by r whole square. Which is now gm by r squared is g naught. Gm by capital R squared is g naught, acceleration due to gravity on the surface of the earth, into 1 plus h by r to the power minus 2. Now, one result in generalized binomial theorem which I want to state here is that if x is numerically much less than 1, if x is numerically much less than 1, then 1 plus x power n is approximately equal to 1 plus nx for any n, n need not be an integer, n can be a fraction, n can be a positive integer, can be a negative integer. 1 plus x power n is approximately 1 plus nx, approximately equal to 1 plus nx when x is numerically much less than 1. Now, the point P could be at a small height above the surface of the earth. Now, when I say small, small or large is only relative, right? When I say h is small, it means it's small compared to the radius of the earth. That's what it means, right? When I say h is small, it means small compared to the radius of the earth. I mean, if the radius of the earth is 6,400 kilometers, then 100 meters would be considered small. But 3,000 kilometers will not be considered small, right? So, now in this case, if h is much smaller compared to r, right? If h is much smaller compared to r, that means if h by r is numerically much less than 1, if h by r is numerically much less than 1, then this becomes approximately equal to g naught into 1 minus 2h by r. 1 plus nx, n is minus 2 here, when h by r is numerically much less than 1. So, this is an approximation. This is not an approximation. This is exact g, but this is an approximation for points P close to the surface of the earth, right? Now, for points inside the earth, how does G vary for points inside the earth? Small r less than capital R, small r less than the radius of the earth. This is the earth. The mass of the earth is capital M. The center of the earth is O. The radius of the earth is capital R. Let's say we will assume that the earth is uniform and perfectly spherical. Let's say there is a particle placed at a distance small r, a particle of mass small m placed at a distance small r from the center of the earth, where small r is less than capital R, which will cause the particle to be inside the earth. Now, if G is the acceleration due to gravity at this point, then that means G is the intensity at this point. That means the force experienced by this particle at P is going to be m into G. If G is the acceleration due to gravity at this point, right? So, if G is the acceleration due to gravity at this point, then the force experienced is m into G. Right? Now, the force experienced by this particle, realize, can be because of two distinct mass regions. One is the mass region contained in a sphere of radius small r. The mass region contained in a sphere of radius small r, that would have a gravitating influence on this small m. And then there is an annulus, spherical annulus of thickness capital R minus small r, which contains a certain amount of mass that can have its own gravitating influence at this mass m. So the net force mg that this small m experiences is because of the mass contained in the sphere of radius small r and because of this shaded mass. The net of both must be mg. Now, as far as this shaded mass is concerned, this shaded mass could be fragmented into several shells. The shaded mass is actually several concentric shells. Do you realize that? Several concentric shells starting from small r equal to small r to small r equal to capital R. Right? You can have concentric shells of this kind. This entire annulus is like a sum of several concentric shells placed end to end constituting this annulus. Yes or no? This entire annulus is constituted out of infinite number of shells of thickness dr, infinite number of shells of thickness dr, concentric, right? Now each of these shells will exert no net force on small m. Each of these shells will exert no net force on small m. So sum of the forces experienced by all these shells on small m will be 0. That means the gravitating influence of this shaded region on this mass small m is 0. No net force is experienced by small m because of this shaded region. Because this entire shaded region is infinity of spherical shells and the mass m lies inside each one of these shells. Right? So, do you understand this fact? Right? That means the only force that this small m experiences is because of the sphere on which it lies, is because of the spherical mass on which it lies. Yes or no? Now, we then have the following. So, we can ignore the presence of the outside region, outside mass. We just have to look at the presence of the mass contained inside this dotted shell, dotted sphere. Now, this is the only relevant mass. This is small m placed at P, and there is the shell of radius small r. Realize that if ms is the mass of this shell, if ms is the of this solid sphere of radius small r, if ms is the mass of this solid sphere, ms is the mass of this solid sphere, then in order to compute the force of interaction between small m and this mass ms, I can replace this entire mass ms by a point mass ms. That means eventually it's like m and ms placed at O, ms placed at O at a distance r. This will give me the force that small m experiences because of this spherical region, because of the spherical mass, solid spherical mass, right? So what's the force? mg is the force. Mg is the force, where g is the acceleration due to gravity at a distance r, and that must be equal to g times small m into ms by r squared. R is the distance from the center of the earth. R is the distance from the center of the earth. Yes or no? Now, we know the total mass of the earth. We know the radius of the earth, and we know small r, but we don't know ms. But we don't know ms, the mass of the sphere on which small m lies. But it's easy to accommodate that, because mass of a sphere is proportional to the cube of the radius. Mass of a sphere will be proportional to the cube of the radius. So can I not say that ms by capital M would be r cube by capital R cube? Could this be said? Capital M proportional to capital R cube. Capital M is the total mass, which will be proportional to capital R cube. ms is the mass of a sphere of radius small r, same density, so will be proportional to small r cube. I hope you understand this. Nahi na? Not very sure. Not sure about this now? Hey, the density of the earth is rho. What is ms? ms would be rho into 4/3 pi r cube. What is capital M? Rho into 4/3 pi capital R cube. Yes or no? ms would be rho density into volume 4/3 pi small r cube. Capital M would be what? Rho into 4/3 pi capital R cube. When you divide, rho and 4/3 pi get cancelled and cube of the radii will come in, right? So now I can replace ms by capital M into r cube by capital R cube right here. And small m anyways gets cancelled. Small m anyways gets cancelled. So that leads to like g times g by r squared into ms. ms is capital M into r cube by capital R cube. That's a g at a distance small r, point inside the earth, right? Which is does it make sense? Huh? This you could also write as gm by capital R squared is g on the surface of the earth. So this is g into small r by capital R. G naught. G naught is gm by capital R squared is g naught, the g on the surface of the earth. So this you could write as g naught into small r by capital R, right? If you put small r equal to capital R, it will become g equal to g naught. Clear? Which means inside the earth, g is proportional to the distance from the center of the earth. That means if you go to the center of the earth, g on the center of the earth will be 0, small r equal to 0. And as you move further and further away towards the surface, small r grows and the value of g grows linearly with small r, isn't it? G is g naught into small r by capital R. So g versus small r inside the earth is a straight line, y equal to mx. The slope of the line is g naught by capital R. So inside the earth, g varies linearly with distance from the center of the earth. Inside the earth, g is a linear function of small r. G is some constant times small r. G naught by r is that constant, the slope of the line. Clear? As you can see, yes. It has the highest value and it has the maximum value on the surface of the earth very clearly, right? So from the center to the surface, it increases linearly and then it decreases as 1 by r square. From the earth above, it decreases as 1 by r square, right? This is how G varies with height and depth. Now, we would look at variation of G caused by the rotation of the earth. In this case, we've not looked into account the effect of the rotation of the earth. Well, if you understand your things right, then the earth has an equator here. This is the equatorial plane. This is the equatorial plane. This is the equatorial plane, right? And then you have a north pole and a south pole. And about the ns axis, the earth spins with an angular speed, omega. It completes one full spin in 24 hours. About the ns axis, it completes one full spin in 24 hours. That means time period of rotation about the ns axis. The time period of rotation about the ns axis is 24 hours or 86,400 seconds, right? So the omega of rotation can be obtained by saying t equal to 2 pi by omega. Omega is 2 pi by t. The angular speed can be obtained. So if you put this as 86,400, you will get radians per second. The spinning velocity, spinning angular velocity of the earth about the ns axis, right? So omega is known. Now we can locate various points on the surface of the earth. We can locate various points on the surface of the earth by a number lambda as shown, by an angle lambda. Different lambdas will give me different points on the, this lambda is said to be the latitude of the point P. This lambda is said to be the latitude of the point P. This is said to be the latitude of the point P. Now, suppose at this point, G was the acceleration due to gravity. Suppose at this point P, G was the acceleration due to gravity when the earth had no omega, when the earth was not spinning, right? When the earth was not spinning, let's say G was the acceleration due to gravity at the point P. If G was the acceleration due to gravity when the earth was not spinning, then a mass small m placed at P experienced a force mg towards O, experienced a force mg towards O when the earth was not spinning. When the earth was not spinning, clear? But now, one thing that I have to mildly put across to you without detailed deliberation is, in a rotating frame of reference, we have what's called an outward centrifugal force, Now this point P, by the way, this mass m is moving in a circle of radius small r. Do you see that? While the earth is spinning, this point M is moving in a circle of radius small r, isn't it? This point P having a latitude lambda. In fact, all points on this circle have the same lambda. All points on this circle, this is parallel to the equatorial plane. This slice is parallel to the equatorial slice, right? So all points on this circle on the surface of the sphere have the same lambda, same latitude, right? And this particular point P, while the earth spins like this point P moves in a circle of radius smaller. So now, by the time the Earth completes one full spin, this point P executes one full revolution. One full revolution, right? That means in the same time, while this describes an angle 2 pi at the center, this also describes an angle 2 pi at its own center. This is the center of the sphere. That means the angular speed of the Earth is the same as the angular velocity of the point P in its own circle. Yes or no? They have the same omega, right? So then this point P is moving in a circle of radius small r with an angular speed omega, given by these many radians per second. Now, this is a fact where there is a little bit of a gray area which I don't want to discuss at length again at this point of time. We say that it's being acted upon by what's called a centrifugal force, which is m omega squared r. This is the centrifugal force. This is the centrifugal force m omega squared r. And this angle is lambda, this angle is lambda. Which means now, the force towards O is no longer mg. Force towards O is no longer mg. It's mg minus component of the centrifugal force in this direction. So the net force towards O is less than mg. Therefore, the acceleration due to gravity decreases here, right? So the net force towards O is no longer mg, but is mg minus the component of the centrifugal force, which is m omega squared r cos lambda. That's the net force towards O, right? When omega was 0, the net force was mg, right? And this in turn must be mass into the g effective because of rotation, mass into the g effective at a latitude lambda because of omega, because of the spin of the Earth. So the g effective is g minus omega squared r cos lambda. Omega squared r cos lambda, yes or no? Right? This angle is lambda. This angle is also lambda. This is r, the radius of the Earth. Do you realize that small r is capital R cos lambda? Small r is capital R cos lambda. Clear? The small r is capital R cos lambda. So replace the small r by capital R cos lambda. So this becomes like a g minus omega squared r cos square lambda. No? Confused? मार दिया था. पैरेललोग्राम लॉ लेके चलो, that's better than ऐसा कराना. It's better to not do it than do what you guys. I understand. I have very special words of praise for these extremely illustrious, enlightened, illuminated men on the planet. Huh? Yeah. I mean, in general, they are equally, they are men or women. There is no way to distinguish between them. So, huh? Yeah. So, I mean, impressive. No? So, very clearly, on the equator, lambda is 0. So then G becomes the least, G minus omega squared capital R. Cos lambda would be 1. When lambda is 0, right? At the equator, lambda is 0. And G effective becomes like by G minus omega squared R. At the poles, there is this. Lambda is 90 degrees, so cos lambda would be 0. G effective is the same as G, which was the G without omega, That means the rotation produces no effect at the poles and has the most pronounced effect at the equator. That's how G varies with latitude. Clear? So this is variation of G with latitude because of omega, because of the spin of the earth, rotation of the earth. There is again a qualitative understanding of the variation of G because of an oblate shape of the earth. The radius at the equator and the radius at the poles differ by roughly 21.72 kilometers. Because of this peculiar shape of the earth, again, G at the poles and G at the equator would be different. Because Gm by R square, the R is different at the equator and poles. It's not exactly the same. They differ by roughly 21.72 kilometers. But again, if you look at the wider view, why we don't look at it with importance is because this 21.72 kilometers is small compared to 6,400 kilometers, which is the radius of the earth. So this small variation in the radius at the poles and the earth can be dumped and ignored, right? So this is how G varies because of omega at different points on the earth, chosen out of various values of lambda, the latitude. So far so good, right? No issues. Variation of G with height, depth, omega, latitude, etc. You understand that. In fact, to tell you very honestly, the real digression on gravitation, I'll give it to you as DVDs. And once you see that, you'll realize that I have not even discussed all this. I don't even talk about variation of G with height, depth, etc. So everything other than what I'm talking is discussed in that DVD. And so obviously I'm making a fool out of you, but then let me do that. Like I said, I'll take this proud privilege of doing it at least one time for you. Next, let's look at some special numbers. This is the Earth, mass capital M, and there is a satellite of mass small m. There is a satellite of mass small m which orbits the Earth in a radius small r. Circular orbit of radius small r of a satellite of mass capital M. Circular orbit of a satellite. Now, let's say if the orbital speed is v0, this v0 is always tangential to the circle, This is the orbital speed v0. Then, to maintain circularity, it would have a centripetal force requirement, which would be mv0 squared by small r. The centripetal force requirement, mv0 squared by small r, must be met by the gravitational pull between small m and capital M. And since this point is outside the surface of the Earth, I can imagine the entire mass of the Earth to be concentrated at the center like a point mass, capital M. So this must be like a G times capital M small m by r square, the centripetal force met by the gravitational pull, the centripetal force met by the gravitational pull, which gives me like the orbital speed in an orbit of radius small r for a satellite as root gm by small r, root gm by small r. If so, this is an important number. This is one of the very many cosmic speeds required. V naught is root gm by small r, the orbital speed at a distance for a circular radius of radius small r, circular orbit of radius small r. Now, what's the total energy of this satellite? While executing this circular orbit, the satellite has kinetic energy half m v naught square, and being at a distance small r from the center of the earth, it has potential energy, right? The total mechanical energy of the satellite GME is kinetic plus potential, Kinetic is half m v naught squared, v naught is the orbital speed. And potential energy is minus g capital M to small m by r, minus g mm by small r. Hey, but mv naught squared is g capital M small m by r, right? mv naught squared is g capital M small m by small r. So this is half g capital M into small m by small r. Which is like minus half gmm by small r, like minus half gmm by small r. That's the total mechanical energy of orbiting satellite, orbiting in a radius small r. And I will come to this fact later. The total mechanical energy of an entity in a gravitational field, if it's negative, that means that entity is bounded to the earth, because the negative number must have come out of potential energy. And if it has potential energy, that means it's not rushed away to infinity. If it was only kinetic energy, the total mechanical energy won't have been negative. But if it's bounded to the earth, it will have kinetic plus potential. And the moment you find that it's negative, that means the potential energy must have been there. And if the potential energy is there, that means it's bounded to the field. It's bounded to the field. So total mechanical energy negative would imply that the entity is bounded to the field, right? At infinity, it will either be positive or zero. It will be positive only because of kinetic energy. Potential energy would be zero at infinity, right? Now, at a distance, there's a mass small m and at a distance r from the center of the earth, I impart a certain velocity Ve to a body. And this velocity is imparted such that the particle escapes the gravitational field of the earth, Now, the total energy of the particle here is kinetic half m Ve square, and there is potential which is minus gmm by r. If it's escaping to infinity, that means its potential energy is becoming zero. Its potential energy is becoming zero. And let's say it's just about able to escape. If it's just about able to escape, that means by the time it reaches infinity, its kinetic energy also would have got completely exhausted, right? So that means if its kinetic energy gets completely depleted and its potential energy becomes zero, that means it must have just about escaped the gravitational pull of the earth. It must have escaped the field. It must have escaped the field. That means this energy must have been the total mechanical energy at infinity, right? Because it's a conservative field. So at infinity, we are saying that it just about is able to reach infinity. That means its kinetic energy is zero, right? And its potential energy anyways is zero. So now we have a velocity VE, which is root 2 gm by r. If you give a body a velocity VE, which is root 2 gm by r, then that body would escape to infinity, escape the clutches of the gravitational force field, right? If you give it a velocity larger than VE, then also it will escape, but by the time it reaches infinity, it will have some remaining kinetic energy. That's all. So this is the minimum velocity that you must impart. This is the minimum velocity that you must impart to a certain body at a distance small r from the center of the earth, so that it's able to escape the gravitational field of the earth. This velocity is called the escape velocity. Minimum velocity that must be imparted so that it escapes the gravitational field of the earth. Now, one fact again which I want to state without proving is if you impart to a certain particle, to a certain body, a velocity v, which is equal to VE, escape velocity, then it escapes the earth, it escapes the gravitational pull along a parabolic path. It escapes to infinity along a parabolic path if the velocity imparted is just the escape velocity. If you impart it a velocity greater than the escape velocity, then it will escape along a hyperbolic path. It escapes to infinity. If you impart it a velocity greater than the escape velocity, then also it will escape, but it will take a different path. It will take a hyperbolic path. For V equal to V escape, it will take a parabolic path. Along V greater than V escape, it will take another path, which is the hyperbolic path, right? V less than V escape means it will remain bounded to the earth. V less than V escape means it will remain bounded to the earth. It will orbit around the earth in one fashion or the other. Clear? Now, the other fact that is easy to notice here is that the escape velocity is root 2 times the corresponding orbital velocity. Do you see that? The orbital velocity was root gm by r. The escape velocity at any point is root 2 times the corresponding orbital speed at that point. Clear? Confused? And when r equal to capital R, when that means on the surface of the earth, the escape velocity will turn out to be 11.2 kilometers per second. From the surface of the earth, if you want a particle to escape to infinity, you must impart it a velocity equal to 11.2 kilometers per second. The important thing is that, so this is the escape velocity on the surface of the earth, from the surface. One, you can impart this velocity to the particle at any angle and it will escape. It does not depend on the angle of projection. This velocity can be imparted at any angle. At any angle. There could be any orientation given to this velocity. and it will escape the gravitational pull. Number one. Number two, it does not depend on the mass of this entity. Mass of this body will not determine the escape velocity. So these are things that you might want to remember. No, it will change now. While it escapes, its potential energy changes, its kinetic energy changes. Realize that its potential energy increases because it becomes less and less negative, right? So kinetic energy must decrease. So by the time it reaches infinity, either its kinetic energy becomes theoretically zero. It will be consumed by the change in potential energy. Gain in potential. There is always gain in potential energy, right? Because when it's bounded to the earth, potential energy is negative. At infinity, it's zero. So it's larger at infinity compared to the earth, right? No, this is the escape velocity only at the instant. This is the velocity at the instant when you impart. After that, it will change. Commensurate with conservation of mechanical energy, it will. Yes, it's already at height. Small r will be 6,400 plus 500, 6,900 kilometers. There's no difference. The small r is general, right? Small r will be capital R plus height h. Root gm by small r is 6,900 kilometers. Now, just a quick mention of what an ellipse is, because if I'm going to talk about a little bit about ellipse, you must at least know what an ellipse is. You know what an ellipse is. Maybe not, right? Essentially, if there are, I'll just give you a brief idea of what an ellipse is. If there are two fixed points S1 and S2, and if a point P moves in a plane along with S1 and S2, such that S1P plus S2P is a constant. That constant is often referred to as 2a. That constant is often referred to as 2a. If P moves in a manner that sum of its distances from two fixed points S1 and S2 is a constant, then the path described by P will be an ellipse. Ellipse. These points S1 and S2 are referred to as the foci of the ellipse. S1 and S2 are called the foci of the ellipse. Now, if let's say I choose the x-axis along S1, S2, if I choose the x-axis along S1, S2, and the midpoint of S1 and S2 as the origin of coordinates, the y-axis would obviously be perpendicular to the x-axis passing through the origin. This would be the y-axis. Now we can show that the equation of the trajectory described by P, if P has coordinates x comma y at any given instant of time, then we can show that the relationship between x and y, that means the locus of the trajectory that P pursues, is like a x squared y a squared plus y squared y b squared equal to 1. That's a locus of the trajectory. Now this is something that I'm not proving, but I'm just stating for the time being. This path is a closed path we can show. This is an ellipse that it describes. This is S1, this is S2, This is the origin O. P lies anywhere along this. The extremities along, see, the line joining S1 and S2 is also called the axis of the ellipse, The extreme points on the axis obtained are A and B. The extreme points on the axis obtained are A and B. This AB is called the major axis of the ellipse, This AB is called the major axis of the ellipse. And has a length equal to 2a, The major axis has a length equal to 2a, which is S1p plus S2p will be 2a, the major axis. The minor axis, A prime, B prime, the extremities witnessed in the y direction, are A prime, B prime. A prime, B prime is the minor axis and is 2b, In general, AO will be OB equal to A, which is called the semi-major axis. If AB is the major axis to A and O is the midpoint of AB, which will also be the midpoint of S1, S2, then OB is OA equals A, which is called the semi-major axis. Of the ellipse. Is the semi-major axis of the ellipse. And OA prime will be OB prime equals B. This is called the semi-minor axis of the ellipse. This is the semi-minor axis of the ellipse. The relationship between B and A, is given as B squared is A squared into 1 minus E squared, where E is a certain number lying between 0 and 1. The relationship between the semi-minor axis and the semi-major axis, is given by B squared is A squared into 1 minus E squared, where E is a property of the ellipse called the eccentricity of the ellipse. It's always a number lying between 0 and 1. B squared is A squared into 1 minus E squared. E is called the eccentricity of the ellipse. If E is 0, then this ellipse becomes a circle because B becomes equal to A and the ellipse transforms into a circle. So a circle is a special ellipse with zero eccentricity. B is less than A. The semi-minor axis will be less than the semi-major axis. Because B squared is A squared minus A squared E squared. So B squared is less than A squared or B is less than A. Not just that, if A is the semi-major axis and E is the eccentricity of the ellipse, then the coordinates of the two foci would be AE0 and minus AE0. Would be the coordinates of the foci. Would be AE0, that means OS2 and OS1 would be AE units in length. This would have coordinates AE0, this would have coordinates minus AE0. Right? So the ellipse has properties, the eccentricity, it has two foci, any point on the ellipse. If you choose any point, then the sum of its distance from S1 and S2 will be the major axis 2A of the ellipse, right? So the ellipse has a semi-major axis, a semi-minor axis, the two foci and the eccentricities. This much you understand? Now for the sake, and do you also understand that the distance of the two foci from the origin here would be AE and minus AE, etc., right? I thought I was feeling so shady teaching you so little. This is not what I would have done in ellipse at all. But then, for the sake of my, I tend to take some pity on these poor fellows. On one hand, there are occasions when I would want to have all of them stand in a queue and castrate them. Yet, there are occasions when, I would just let them go. God forgive me. I'm being on record. I can't even keep track of what I say in each class, and down the line people come and tell me, I saw this recording of yours, and sir, there was some parliamentary stuff there. I hope down the line whoever watches this DVD would be mature enough to forgive me for these nuances. All right. Now, once we understand some of these facts about the ellipse, then let me state the following. I spoke of the orbital speed, right? At a distance small r from the center of the earth, if a particle was launched with a speed v equal to the orbital speed, what would it have done? It would have executed a circular orbit of radius small r centered at the center of the earth, right? That's what it would have done. If you would have given it a speed equal to orbital speed, it would have orbited in a circle of radius small r around the center of the earth. This is what, where v naught is root gm by small r, right? If you imparted a speed less than the orbital speed, what would happen? The question is, if you imparted a speed, again without proof, something that I want to offer, if you impart it a speed less than the orbital speed, then it can no longer undertake this circular trajectory, right? What it does is, with the center of the earth as one of the foci, it will undertake an elliptic trajectory. If v less than v naught, then an elliptic trajectory with O as one focus, the focus that is farther away, right? Compared, if this is a point on the ellipse, then there would be a focus which would be closer to P, there would be a focus away from P. So O, the center of the earth, would be the focus further away from the point P, right? So it undertakes an elliptic trajectory with O as one focus, the center of the earth as one focus, it will undertake a elliptic trajectory. Now, two things could happen depending on how much smaller it is compared to V naught. We could have had an elliptic trajectory of this kind. This would have been the proposed elliptic trajectory. Which would prematurely terminate because it strikes the earth. This is the center of the earth. This would become one focus of the elliptic trajectory. And depending on what V is, how much smaller it is compared to V naught, one possibility is, well, it started to execute this ellipse. It wanted to execute this ellipse, with this velocity V, which is less than V naught. It would have liked to execute this ellipse with this focus, but it hits the surface of the earth and it gets prematurely terminated. So only a portion of the ellipse is executed. Only a portion of the ellipse gets executed. That's one possibility. The other possibility could be the following. With V less than V naught, again depending on how much less, it could actually execute a full ellipse with O as one of the foci, it could actually execute a full ellipse. This is another possibility. O as one of the foci. Two possible. So if the velocity imparted is less than the orbital speed, then either it will execute an incomplete ellipse or it could execute a complete ellipse with the center of the earth being one of the foci. Right? No. So when it strikes the earth, this is one case. When it does not strike the earth, this is another case. It only depends on how much smaller it is compared to the orbital speed, right? Now, V equal to V naught we have covered, V less than V naught we have covered, V equal to escape velocity we have covered, V greater than the escape velocity we have covered. But what when V lies between the orbital speed and the escape velocity? When it's greater than the orbital speed but less than the escape velocity, it's obviously not going to escape, so it will remain bounded. It will remain bounded. Any velocity less than the escape velocity will cause the body to remain bounded to the gravitational field, right? So that will produce another elliptic path. If V is greater than the orbital speed but less than the escape velocity, I imparted a velocity V which is greater than the orbital speed but less than the escape velocity, then it takes up an elliptic trajectory with O as one of the foci. It takes up an elliptic trajectory with O as one focus, center of the earth as one focus. If the velocity lies between the orbital speed and the escape velocity, then an elliptic trajectory, I know it's not a very beautifully drawn ellipse, but pardon me for that. That is what it would do. V equal to escape, parabolic and infinity. V greater than escape, hyperbolic and infinity. Clear? Which one? Well, in this case, I'll just come to that discussion. You'll be able to hash it out yourself. Let me just discuss a few things. You'll realize how to figure out a closer or a further focus. Just a little more discussion, and it'll be on you'll be on your own, right? Now, in an elliptic path, I'll just draw the ellipse like this rather than like this because it's inconvenient to draw it that way. Let's say there was a fixed mass m replaced by a point mass capital M, right? And there was in the gravitational field produced by capital M, there was another mass which was executing an elliptic path with a certain mass capital M as one focus. With one focus, there was another mass small m executing an elliptic path. The center of this ellipse is O. This is the major axis of the ellipse. This is the center of the ellipse. Now, at any given instant, when the mass small m is at a certain point P, then it experiences a force F whose line of action will pass through capital M, whose line of action will pass through capital M, yes or no, right? When this force passes through capital M, it produces no torque about capital M. If it produces no torque about capital M, that means the angular momentum of small m about capital M must be constant. That's the law of conservation of angular momentum. That's the law of conservation of angular momentum. That means the angular momentum L of this mass m, while it executes this ellipse L about capital M, will be a constant, L about capital M will be a constant. Clear? Because no net torque about capital M, because the gravitational pull must pass through capital M at all instants. No net torque, right? Let's say some instant it's at a distance small r. Some instant this particle small m is at a distance small r from this mass capital M, under whose influence it executes this ellipse. Now, let's say the angular speed, at every point it has an angular speed, right? The angular speed of this mass m is omega, let's say, when it's at t. That means in a small time dt, this radius vector will remain practically r, small r in a small time dt, whereas it's going to describe an angle d theta at the center. This radius vector describes an angle d theta at the center in a small time dt. In a small time dt, it describes an angle d theta at the center. This is practically like a circular arc. Whose center is capital M and whose radius is small r, and the sector angle is d theta, right? Yes or no? No issues, right? And then the omega is going to be the angle described at the center in time dt. That's omega. Right? The angular momentum of this particle about m, would be moment of inertia about m into r squared. Moment of inertia about m, which is mr squared. Moment of inertia about this point, which is small m into r squared. Moment of inertia is mr squared about capital M into omega. That's going to be the angular momentum about capital M. Yes or no? I omega. Angular momentum about this point is going to be I, which is mr squared, into omega. Omega is the angular speed at this instant. Now, at different instants, r would be different at different points. Omega will also be different at different points along this elliptic journey. But L will be the same. Angular momentum about capital M will be the same. The angular momentum remains preserved because of no net external torque about capital M, right? That means this is a constant. Which is like a mr squared. Omega is like a d theta dt. That means r squared d theta dt. Is L by m, which is a constant because L is the angular momentum of this particle in this elliptic journey. M is the mass. Both are constant. So that's a constant, L by m, which means half of r squared d theta dt is L by 2m, which again is a constant. Yes or no? Now look at this sector. This sector centered at capital M P to P prime, P to P prime. This angle is d theta. This is R. This is R. Then this area is half of R squared into d theta. You know that. Half of R squared into the angle described at the center. That would be this area, dA. This would be dA, the area at the center. Half of R squared into d theta. That's the area. You understand this, right? Huh? That's the area of this sector, half of R squared into d theta. That means this half of R squared into d theta dt is what? dA dt is dA dt, because half of R squared into d theta is dA. So this is dA dt. Huh? That's a constant. But dA dt is what? Rate at which area is described about the focus. Rate at which area is described about the focus where capital M is located. That means that's a constant. That means equal areas are described in equal intervals of time. If you have the same dt, then the same dA will be described about M. About M. Right? Basically then what it really means is, if a particle executes an elliptic trajectory, about capital M, then in a given time, let's say, if it describes this area, if it moves from P to P prime in a given time, and it describes this area, and now it's at Q, and you give it the same time as it took to go from P to P prime, it goes from Q to Q prime, and in the same time it will describe the same area. Rate at which it describes area about the focus M, where the mass capital M is located, is a constant. The rate at which it describes the area about capital M, the focus where the mass M is located, is going to be a constant. It describes equal areas in equal intervals of time. Right? That's one thing. In fact, that's one of the Kepler's laws. If capital M was one of the foci, the sun, then the Earth, let's say, of mass small m, or any planet mass small m, will execute an elliptic path about the sun, with the sun being one of the foci, and it will describe equal areas about the sun in equal intervals of time. That's the aerial law. Law of areas. That's the law of areas. And this is not just about the sun and the planet. Any elliptic path around a gravitating mass will subscribe to this requirement. Clear? The aerial requirement, equal areas and equal intervals, and realize that it's only a consequence of the law of conservation of angular momentum, right? Now, in this elliptic path, I mean, you could have this M as the sun or any other gravitating mass, and this could be a planet or any other mass. Does not matter. If it's an elliptic path, the same physics holds good, right? Very clearly, this is the point A, where the mass small m is closest to the sun or any other gravitating mass, and this point A is called the perigee. And this point B, where it's farthest from this mass, is called the apogee. Perigee and apogee. Now, when it's closest to the earth, these small r's are the least, right? The small r's are the least. That means it has to have a larger velocity. Again, why? Because, let's say, when it's at A, its distance from capital M is R1. When it's at B, its distance from capital M is R2, right? And let's say at A, it has a velocity V1, which is perpendicular to the axis and tangent to the ellipse. The velocity at any given instant would be tangent to the ellipse. So in this case, it's tangent to the ellipse, which is V1. At B, it's tangent and V2. Then the angular momentum that this has, see, what is its linear momentum? mv1. Angular momentum is going to be mv1 into r1, right? So angular momentum at A is like a mv1 r1. That's the angular momentum at A about capital M. The angular momentum at B about capital M is going to be m v2 r2, and the two must be the same, right? So v1 r1 is v2 r2. So if the r is small, the v is large. So when it's closer to capital M, closer to focus, it will have a higher velocity. When it's farther away from the focus, it will have a lesser velocity, right? Not just that, very often, not only do we apply the law of conservation of angular momentum, we also apply the conservation of total mechanical energy. The mechanical energy at A is potential plus kinetic, which is how much? Half m v1 squared as kinetic, and potential is minus gm m by r1, minus gm m by r1 is going to be the potential energy. This must be equal to the total mechanical energy at B, which is like a half m v2 squared minus gmm by r2. Clear? Now, very clearly, using these two equations, you can solve for the velocities at the perigee and apogee using the law of conservation of angular momentum and conservation of mechanical energy. You can solve for V1 and V2 in terms of distances R1 and R2 of the gravitating of the mass of the focus from the perigee and the apogee respectively. And you would know what's happening at the extremities of the major axis. What's happening at the extremities of the major axis, right? Now, in fact, once you solve for this, then you would also have L available. So if you have V1 available, you also have the angular momentum available. And once you have angular momentum available, realize that we got dA dt as L by 2m. As L by 2m, so L is known to you now. If V1 and V2 are known, then L is known to us. So L by 2m is dA dt is what we worked out a little while ago. Constancy of the aerial velocity, rate of description of area. And once you have this, then what you could do is, once you have the rate at which area is described, then you can find the time it takes to describe the full area of the ellipse. Full area of the ellipse. You can find the time it takes to describe the full area of the ellipse. Realize, this is the rate at which area is described about m, right? In a certain time, it will describe, let's say, this is where it was. It will go from P along the entire ellipse and come back to P. And when it goes from P and comes back to P, it takes a time equal to T, which is the time period of revolution, time taken to complete one full revolution, right? Now, in a full time T, what area does it describe? It describes this area, this entire area, right? And at what rate? At the rate L by 2m. So, do you realize that the time it takes will be the area of the ellipse, entire ellipse, divided by the rate at which area is described, which is L by 2m, yes or no? Now, again, if small a and small b are semi-major and semi-minor axes of the ellipse, we can show using integration that the area of an ellipse is pi AB. The area of an ellipse is pi AB. A is the semi-major axis and B is the semi-minor axis. Then pi AB is the area of the ellipse. Pi AB is the area of the ellipse. So you can replace this area by pi AB, and L by 2m is dA dt. You will get the time of full revolution around the gravitating mass capital M. Now, one thing. If this is O, this is A, then OA is the semi-major axis, like I said, is small a. It's a semi-major axis, this is small a. And this is where one of the foci is, that means this length is AE, like I said, distance from the midpoint of the major axis to each foci would be AE, and this is R1, this is R1. So R1 is A minus AE. Do you realize that R1 is A minus AE? Clear? R1 is A minus AE. This is A. This is AE. This is because this is one of the foci. This is A. So this is R1 from one extremity of the major axis. So this is going to be A minus AE. A minus AE. Whereas this was capital M. This was B. This was O. This is A. Realize that this was R2, distance of B from M was R2, and this is AE. So what's R2? A plus AE. R2 would be A plus AE. So in this equation, you can plug in R1 and R2 as A minus AE and A plus AE, and you can solve for V1 and V2 entirely in terms of the eccentricity E, entirely in terms of the eccentricity E, which is the quality of the path described. So everything, once you solve everything in terms of the required entities, again I will not budge too much into this, what you would get is plug in all of this, then you're going to get the following. You will get T squared proportional to A cubed. You will get T squared square of the time period proportional to cube of the semi-major axis. You will get square of the time period proportional to cube of the semi-major axis of the ellipse of description, which again is one of the Kepler's laws, which in general could be applied to any mass. Got me? So then, in a nutshell, we are taken care of. As far as gravitation is concerned, this should entirely sum up your school requirements. In principle, nothing bizarre about it, really simple stuff, and I hope you will be able to handle your school exam with this, right? Anything else that you have in mind on gravitation which you want me to quickly talk about, which is there for school and I have somehow... Newton and Kepler's laws. The relation between Newton and Kepler's law. Oh, you want... We have actually proved Kepler's laws only, and we have used... These are all consequences of Newton's laws. I mean, if I have applied energy, this is out of Newton's laws. It's just that I didn't use names and I proved it differently from what your book must have used. Energy and angular momentum to arrive at Kepler's laws. These are Kepler's laws. So I don't understand what the distinction is. This is Kepler's laws only, proof. And those are Newton's laws only. And I'll tell you, those are assholes. Because this is what they have done. I'll tell you. I keep forgetting that I'm being observed. Going to be observed down the line, perhaps by many more people, but I'm sorry. Alright. CmPO4 है वो लोग क्या किए पता है तुमको? इलिप्टिक पाथ भी नहीं लिए हैं ससुरे लोग, वो लोग सर्कुलर पाथ लिए हैं, GMM बाय आर स्क्वायर, वो तो कुत्ता बनती सॉरी